This is the video for part 2 of section 7.5, the symmetric and alternating groups. In this video we're going to be looking at the alternating groups, but it's going to take us a little while to get there. A two-cycle is called a transposition. As we'll see, transpositions have some interesting properties and play an important role in classifying permutations. First note that for any transposition AB times itself is equal to the identity, which implies that AB inverse is equal to AB. This shows that each transposition is its own inverse. And we can use this to determine the inverse of a product of transpositions. For example, we want to show that the inverse of the product of transpositions 1, 2, 3, 4, 1, 4, 1, 3 is 1, 3, 1, 4, 3, 4, 1, 2. Now, in a group, the inverse of a product is the product of the inverses in reverse order. This is one of our theorems from section 7.2. For any elements A and B in a group, AB inverse is equal to B inverse A inverse. This can be generalized to a product containing more than two factors. Using this result, the inverse of 1, 2, 3, 4, 1, 4, 1, 3 is equal to the inverse of the factors in the product in reverse order, so that will be the inverse of 1, 3 times the inverse of 1, 4 times the inverse of 3, 4 times the inverse of 1, 2. And now the inverse of each of the transpositions is the transposition itself, so this will just be 1, 3, 1, 4, 3, 4, 1, 2. Now a similar argument shows that in general, the inverse of a product of transpositions equals the product of the same transpositions in reverse order. For all transpositions sigma 1, sigma 2, up to sigma sub n, the inverse of the product sigma 1 times sigma 2 times sigma 3 up to sigma n will be sigma n minus 1 down to sigma 3, sigma 2, sigma 1. We next want to show that every permutation can be written as a product of transpositions. The following example illustrates this. So we want to write the 5-cycle 1, 2, 3, 4, 5 as a product of transpositions. And we claim that this 5-cycle is equal to the product 1, 2, 2, 3, 3, 4, 4, 5. To verify this, let's compute the product on the right-hand side. So we'll start with the element 1. So in 4, 5, 1 is fixed, in 3, 4, 1 is fixed, and 2, 3, 1 is fixed. So the only transposition that affects 1 will be the very first one, 1, 2. So we'll start with 1, and 1, 2 moves 1 to 2, so 1 gets mapped to 2. Next we'll look at 2. Well, the fourth transposition on the left keeps 2 fixed, as does the third, and the second one moves it. So 2 maps to 3, and the first transposition will now fix 3. So the result will be 2 maps to 3. Now we'll look at the effect of 3. So in 4, 5, 3 is fixed. In 3, 4, 3 maps to 4. And then in 2, 3, 4 is fixed. And in 1, 2, 4 is fixed. So 3 maps to 4. And now we'll look at 4. So in the fourth transposition on the left, 4 maps to 5. And then in the other 3, 5 is fixed. So 4 maps to 5. Now we want to look at the effect of 5. So in the fourth transposition 5 maps to 4. And then 4 maps to 3. And then 3 maps to 2. And finally 2 maps to 1. So that tells us that 5 maps to 1, which closes off our cycle. And so that verifies that equality. And this leads us to a theorem, theorem 726, which tells us that every permutation in S sub n is the product of transpositions. To prove this, first note that by theorem 724, we know that every permutation can be written as the product of disjoint cycles. It then suffices to show that each cycle can be written as a product of transpositions. So let's suppose that A1, A2, A3, down to A sub k minus 1, A sub k is an arbitrary cycle. As in the example, we can verify that we can write this k-cycle as the product a1, a2, a2, a3, down to a sub k minus 2, a sub k minus 1, a sub k minus 1, a sub k. And this proves the theorem. We've now written that our k cycle is a product of transpositions, and we know that every permutation is a product of cycles. Now, it can be shown that the factorization of a permutation as a product of disjoint cycles is unique, except for the order of the cycles. However, the factorization as a product of transpositions is not unique. For example, let's decompose the 3-cycle 1, 2, 3 and the 4-cycle 1, 2, 3, 4 as products of transpositions. Now, as in the previous example and in the theorem, we can write the 3-cycle 1, 2, 3 as the product 1, 2, 2, 3. But we can also verify that this 3-cycle 1, 2, 3 can be written as 1, 3, 2, 3, 1, 2, 1, 3. And to check this, let's look at the effect of the product on the right side with each of the elements 1, 2, 3. So first, the rightmost transposition maps 1 to 3, and then 3 is fixed in the third transposition, but in the second transposition 3 maps to 2, and then in the first transposition 2 is fixed. So on the right side 1 is mapped to 3 and then 3 to 2, so that tells us that 1 maps to 2. Now let's look at 2. So in the fourth transposition on the right 2 is fixed, and then in the third 2 is mapped to 1, and in the second 1 is fixed, and in the first 1 is mapped to 3. So 2 gets mapped to 1, 1 gets mapped to 3, so that tells us that 2 maps to 3. And then finally, let's look at 3. Well, in the fourth transposition, 3 maps to 1. In the third, 1 maps to 2. And then in the second, 2 maps to 3. And in the first, 3 maps to 1. So we get 3 maps to 1, 1 to 2, 2 to 3, 3 to 1. So the net effect is 3 maps to 1. And that's our 3-cycle. So that verifies that equality. And similarly, we can write our 4-cycle, 1, 2, 3, 4, as the product 1, 2, 2, 3, 3, 4. And we can also verify that this 4-cycle can be written as the product 1, 2, 2, 3, 1, 3, 3, 4, 1, 4. So there's multiple ways we can write a cycle as a product of transpositions. Now, even though the factorization of a permutation as a product of transpositions is not unique, the number of transpositions in such a factorization turns out to be always even or always odd. And we'll say that a permutation in S sub n is even, provided that it can be written as the product of an even number of transpositions, and odd, provided that it can be written as the product of an odd number of transpositions. For instance, in the preceding example, we wrote 1, 2, 3, the 3-cycle, as the product of 2 transpositions and as the product of 4 transpositions. So this 3-cycle 1, 2, 3 is even. We also wrote the 4-cycle 1, 2, 3, 4 as the product of 3 transpositions and as the product of 5 transpositions. So that tells us that the 4-cycle 1, 2, 3, 4 is odd. Now we want to show that no permutation is both even and odd. In order to prove this, we first prove the following lemma. This is lemma 7.27, and this tells us that the identity permutation in S sub n is even, but not odd. And to prove this, well, this is going to be quite a long proof and fairly complicated, but let's go ahead and dive into it. So first note that the identity permutation, which we can write as a 1-cycle just containing 1, can be written as the product of 2 transpositions. So the 1-cycle 1 is equal to 1, 2, 1, 2. So that tells us that the identity permutation is even. We then need to show that it is not odd. And to do this, we'll use a proof by contradiction. So we'll suppose that our identity permutation is odd. This means that 1 can be written as a product of an odd number of transpositions. So we can write it as tau k, tau sub k minus 1, down to tau sub 2, tau sub 1, where the k, the number of transpositions, is odd, and each of the taus is a transposition. We then need to derive a contradiction. So let's suppose that C is a symbol that appears in at least one of these transpositions. And let's suppose that tau sub r is the first transposition reading from right to left in which C appears. And let's say that tau sub r is the transposition CD. Then C does not appear in the transpositions to the right of tau sub r, so it does not appear in tau sub r minus 1 down to tau sub 2, tau sub 1, and so is left fixed by these transpositions. In the case that r is equal to k, then C is fixed by tau sub k minus 1 all the way down to tau sub 1, which is all the transpositions except for tau sub k. But then the product tau sub k minus 1 down to tau sub 2, tau sub 1 maps C to D, which is a contradiction since the product is supposed to equal the identity. So that tells us that r cannot be equal to k, and therefore r is strictly less than k. Now let's consider the transposition tau sub r plus 1. So this is the one that appears directly to the left of tau sub r. So it comes just before tau sub r. Now tau sub r plus 1 must have one of the following forms where x, y, c, and d represent distinct elements of our elements 1, 2, up through n. So one possibility is tau sub r plus 1 is xy, and so this means that it just contains two completely different elements from tau sub r. It doesn't contain either c or d, it contains two other elements, x and y. The next possibility is it contains d but not c, so it's going to be a transposition of the form xd. The third possibility is it contains c but not d, so it has the form cy. And the fourth possibility is that it's equal to cd itself. So there are then four possibilities for the product tau sub r plus 1, tau sub r. In the first case, we have xy, cd. In the second, xd, cd. In the third, cy, cd. And in the fourth, we have cd, cd. So now we're doing a proof by contradiction, so we want to show that in each of these cases, we're going to obtain a contradiction. So let's consider each of these four cases. So case 1, let's suppose that tau r plus 1, tau sub r is xy, cd. Since xy and cd are disjoint, then they commute. So xy cd will be equal to cd xy. And what we can do then is we can replace xy cd in the product with cd xy without affecting the product. And what this does is it moves the first appearance of c one transposition to the left. Now case 2, let's suppose that tau sub r plus 1 tau sub r is equal to xd cd. Now you can compute and you can show that xd cd is equal to xc xd. So that's a fairly straightforward calculation. Just look at what each side does to each of the elements x, c, and d. And this means that we can replace the product xd cd in the product for the identity with xc xd. And now what this does is this again moves the first appearance of c one transposition to the left. So originally the first appearance of c was in the tau sub r spot, and now we're moving it to the tau sub r plus 1 spot. Now case 3, we'll suppose tau sub r plus 1 tau sub r is cy cd, and note that cy cd is equal to cd dy, and again you can just verify this computation. And this means we can replace the product cy cd in the product for the identity permutation with cd dy, and this again moves the first appearance of c one transposition to the left. So in these first three cases, we can replace our two transpositions tau r plus 1 tau sub r with two other transpositions that will result in moving the first appearance of this element c one transposition to the left. So instead of appearing in the r spot, it's going to appear in the r plus first spot. Now each time we apply the procedure in these first three cases, we can imagine sort of doing it over and over again, we move the first appearance of C one transposition to the left. We can keep doing this as long as one of these first three cases occur. At some point, however, case 4 must occur. Otherwise, we could keep moving C to the left until its first appearance is in the leftmost permutation, which was tau sub k. Now, as shown above, this results in a contradiction, because our product is equal to the identity permutation, and so we can't have the first appearance of C to be in the leftmost permutation. So we can then assume that case 4 has to occur. We can't have only cases 1, 2, and 3. So case 4, we're supposing that tau sub r plus 1, tau sub r, is equal to CD, CD. Now, since tau sub r plus 1, tau sub r equals CD, CD is just equal to 1, the identity, then we can delete these two transpositions from the product and write our identity permutation as a product of two fewer transpositions than originally. We can now start over again with another element that appears in a transposition in the product. And by repeating this procedure for each such element, we can delete transpositions 2 at a time. Since we suppose that there were an odd number of transpositions in the product to begin with, we must eventually obtain a product with a single transposition. So we'll eventually obtain the identity permutation written as a transposition AB. But this is a contradiction, since a single transposition will not equal the identity. And so this proves the lemma. Okay, so this is a fairly complicated proof, and I wouldn't be too concerned about, don't expect to reproduce it on your own. Okay, so we want to use the lemma to prove theorem 7.28. And this says that no permutation in S sub n is both even and odd. So for the proof, we're going to use another proof by contradiction. So we'll suppose there exists a permutation alpha in S sub n that is both even and odd. This means that alpha can be written as a product sigma 1, sigma 2 down to sigma sub r, and as a product tau 1, tau 2 down to tau sub s for some odd integer r and even integer s in transpositions sigma sub I and tau sub j. So since alpha is even, we can write it as a product of an even number of transpositions, and since alpha is odd, we can write it as a product of an odd number of transpositions. We then need to derive a contradiction. Well, what we can do is look at the identity permutation. So this will be equal to alpha times alpha inverse, and we can substitute sigma 1, sigma 2 down to sigma sub r for alpha, and then we can substitute tau 1, tau 2 down to tau sub s for alpha in the alpha inverse term. And now the inverse of a product is the product of the inverses in reverse order. So this will be the product sigma 1, sigma 2 down to sigma sub r, tau sub s inverse down to tau sub 2 inverse, tau sub 1 inverse. And each of the taus is a transposition, so the inverse of a transposition is just the original transposition. So this will be sigma 1, sigma 2 down to sigma sub r, tau sub s down to tau sub 2, tau sub 1. And now we have r plus s transpositions in this product, and since r is odd and s is even, then r plus s is odd. So this gives the identity permutation 1 written as a product of an odd number of transpositions. But by the lemma, this is a contradiction. And this proves the theorem. Now the set of all even permutations in S sub n forms a subgroup of S sub n as shown in our next theorem. And this subgroup is denoted A sub n and is called the alternating group of degree n. So theorem 7.29 says that the set A sub n of even permutations in S sub n is a subgroup of order n factorial over 2. So its order is half the order of S sub n. So to prove this, we need to show that A sub n satisfies our three conditions for a subgroup, SG0, SG1, and SG2. So for SG0, we need to show that A sub n is non-empty. And since the identity permutation 1 is even, then 1 belongs to A sub n, so that tells us that A sub n is non-empty. So SG0 is satisfied. Next, we have SG1, closure, for all alpha beta in A sub n. The product alpha beta is in A sub n. So let's suppose that alpha and beta are arbitrary even permutations. Then alpha is equal to sigma 1, sigma 2 down to sigma sub r, and beta is equal to tau 1, tau 2 down to tau sub s for some even integers r and s and transpositions sigma sub I and tau sub j. So we can write alpha as a product of an even number of transpositions, and we can write beta as the product of an even number of transpositions. Then the product alpha beta will be sigma 1, sigma 2 down to sigma sub r, tau 1, tau 2 down to tau sub s, and this will be the product of r plus s transpositions. Now since r and s are even, then their sum, r plus s, is even, so this tells us that alpha beta is even, so it belongs to A sub n. And therefore A sub n satisfies SG1. Next we have SG2, containment of inverses. We need to show for all alpha in A sub n, alpha inverse is in A sub n. So let's suppose that alpha is an arbitrary even permutation. Then we can write it as a product of an even number of transpositions. So alpha will be sigma 1, sigma 2 down to sigma sub r for some even integer r and transposition sigma sub I. Then alpha inverse will be that product inverse, and this will be the product of the inverses in reverse order. So this will be sigma sub r inverse down to sigma sub 2 inverse, sigma sub 1 inverse. And again, these are transpositions, so the inverse of a transposition is the original transposition. So this will be sigma sub r down to sigma sub 2, sigma sub 1. And so this gives alpha inverse written as a product of an even number of transpositions, which implies that alpha inverse is even, so belongs to A sub n. And therefore A sub n satisfies SG2. So we've verified our three conditions, and so thus A sub n is a subgroup. Now the second part of the theorem was that the order of A sub n is n factorial over 2, and this is left to one of the exercises. Okay, for example, let's list the elements of S3 and A sub 3. Okay, now using the two-row notation for permutations, we've listed the elements in S3 before. So S3 is equal to these 6 permutations. Now using cycle notation, we can write S3 much more compactly as the identity, which is the one cycle 1, and then we have 3 2 cycles, 1 2, 2 3, 1 3, and then 2 3 cycles, 1 2 3, 1 3 2. And the even permutations will be the identity and the 3 cycles. So A sub 3, the alternating group of degree 3, will consist of the identity permutation 1 and the 3 cycles 1 2 3, 1 3 2. And this completes the video for part 2 of section 7.5, and this finishes off chapter 7.